They told him the Panther was invincible from the front. Oberleutnant Klaus Becker had believed it absolutely. He had commanded Panthers since Kursk, had watched Soviet shells bounce off the sloped glacis plate, had seen his long 75mm gun punch through 34s at ranges, where return fire was impossible. The mathematics of armoured warfare seemed to favour his tank in every engagement. Sloped armour at 55 degrees, effective thickness approaching 140mm against kinetic projectiles. A gun that could penetrate 120mm. Of vertical armour at 1,000 metres. Speed, protection, and firepower in balance. Now, in late September 1944, Becker sat in a tent at the captured enemy equipment facility near Isigny-sur-Mer in Normandy, his hands still wrapped in bandages, from burns sustained when his Panther, brewed up 3 weeks earlier. American technical intelligence officers had brought him here, not to a prisoner of war camp, but to this collection of destroyed German armour arrayed in rows like monuments to obsolescence. They wanted him to see something. They wanted him to understand. An American, captain, a mechanical engineer from Detroit before the war, gestured toward a Panther Ausführung G that had been hit during the fighting near Aracourt. The tank sat at an angle on its broken suspension, the entire right side of the turret peeled back like opening a can. The penetration hole in the frontal turret armour was enormous, nearly 4 inches across, with the characteristic petaling that indicated complete perforation at high velocity. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The captain spoke in accented but serviceable German. "We want you to examine this vehicle, walk around it, tell us what you see." Becker stood slowly, his body still aching from the concussion that had knocked him unconscious when his own Panther was hit. He approached the destroyed tank with the careful attention of a man who had spent 2 years living inside such machines, who knew every weld seam and armour joint, every vulnerability and strength. What he saw made no sense with what he had been taught. The penetration was not a glancing blow that had found a weak point. It was not a shot through the thinner side armour or the vulnerable turret ring. This was a direct frontal hit on the mantlet, the thickest armour on the entire vehicle, 110mm of face-hardened steel, and the projectile had gone through as if the armour were sheet metal. He had seen Panthers destroyed before. At Kursk, a few had been knocked out by Soviet 85mm guns at close range, usually through the side armour during chaotic armoured melees. In Normandy, British 17-pounders had claimed several Panthers, though typically these required flank shots or hits on the thinner lower glacis plate. But this devastation, this complete perforation of frontal armour, this represented something different. This represented a weapon system that invalidated the fundamental protection his tank was designed to provide. The American captain watched him, process the implications. "The gun that did this," he said quietly, "is our 90mm M3. We mounted it in the M26 Pershing heavy tank and in the M36 tank destroyer. It fires a 24-pound armour-piercing projectile at 2,800 feet per second. At the range, this Panther was engaged, approximately 800 meters. The penetration capability exceeds 170mm of homogeneous armour. Your frontal turret armour, even face-hardened, offers no protection." Becker said nothing. He walked around the destroyed Panther, his engineer's mind cataloguing the damage, the spalling on the interior that had killed the crew instantly, the way the armour had failed, not through shattering but through clean penetration. Everything he had believed about his tank's invulnerability was predicated on facing Soviet 76mm guns or American 75mm guns, weapons that struggled against the Panther's frontal aspect. This was something else entirely. The Panther had been born from trauma. In the summer of 1941, when Operation Barbarossa launched Germany's invasion of the Soviet Union, German armour crews encountered the 34 medium tank and experienced their own moment of technological shock. The 34's sloped armour defeated the standard German 37mm and 50mm guns at normal combat ranges. Its 76mm gun could destroy any German tank in service. Its wide tracks and powerful diesel engine gave it mobility across terrain that bogged down German panzers. The shock was profound. German tankers had grown accustomed to material superiority. The Panzer III and Panzer IV had dominated in Poland and France against inferior opposition. Now, suddenly, they faced a tank that outclassed them in armor, armament, and mobility. Crews reported instances where 34s absorbed multiple hits and continued fighting. The psychological impact was severe enough that frontline units sent urgent requests for new weapons and new tanks capable of meeting the Soviet threat. The German response was characteristically thorough. In November 1941, the Waffenamt, the German Army Weapons Agency, issued specifications for a new medium tank. The requirements were specific and derived directly from combat experience against the 34. The new tank would weigh approximately 35 tons, mount a gun capable of defeating the 34's armor at 1,000 meters or greater, incorporate sloped armor for improved protection, and maintain sufficient speed and reliability for extended operations. Daimler-Benz and Maschinenfabrik Augsburg-Nürnberg, known as MAN, both submitted designs. The Daimler-Benz proposal closely resembled the 34, with rear-mounted engine and turret positioned far forward. The MAN design retained a more conventional layout, with front-mounted transmission and centrally positioned turret. After extensive evaluation, the MAN design was selected, primarily because it could be produced more quickly using existing manufacturing infrastructure and required less radical changes to crew training and doctrine. The first prototype, designated VK3002, was completed in September 1942. Testing revealed a vehicle that met or exceeded the original specifications. The sloped frontal armor, 80 mm thick, set at 55 degrees from vertical, provided effective protection equivalent to 140 mm against most anti-tank weapons then in service. The Rheinmetall Borsig 7.5 cm KWK 42L/70 gun offered outstanding armor penetration, capable of defeating 120 mm of vertical armor at 1,000 meters with standard armor-piercing ammunition. The tank achieved a top speed of 46 km per hour on roads, despite weighing 44.8 tons in combat configuration, testimony to the powerful Maybach HL 230P 30 engine producing 700 horsepower. The interleaved road wheel suspension system, using Schachtelaufwerk overlapping bogies, provided excellent cross-country performance and crew comfort compared to earlier German designs. Production began in January 1943 at MAN's facilities in Nuremberg and at Daimler-Benz plants in Berlin. Maschinenfabrik, Niedersachsen, Hanover, and Henschel in Kassel joined production later that year. The initial production rate was modest, just 26 tanks delivered in January, increasing to 86 in February. By May 1943, production reached 150 tanks per month, and the Panther began reaching frontline units in meaningful numbers. The first combat deployment came at Kursk in July 1943 during Operation Citadel, Germany's last major strategic offensive on the Eastern Front. The Panthers were organized into special formations, including the entire XLVEII Panzer Corps, which fielded 200 Panthers for the offensive. The initial combat performance was mixed. Mechanical reliability problems plagued the early Ausführung D models. Transmission failures and engine fires sidelined numerous tanks before they could engage the enemy. Final drives broke under the stress of the tank's weight, combined with aggressive maneuvering, but when the Panthers functioned properly, they proved devastatingly effective. Soviet tank crews reported that Panthers could engage and destroy 34s at ranges exceeding 1,500 meters, well beyond the effective range of Soviet return fire. The sloped armor proved resistant to most Soviet anti-tank guns. A single Panther, commanded by Oberfeldwebel Ernst Bachmann, claimed to have destroyed 15 Soviet tanks in a single engagement near Kursk, picking them off, methodically, from a hull-down position. By late 1943, after addressing the early mechanical problems through design modifications in the Ausführung A variant, the Panther had evolved into what many German tank crews considered the finest medium tank in the world. version incorporated a new cupola for the commander with better vision blocks, a ball-mounted hull machine gun replacing the earlier letterbox mount, and strengthened final drives that reduced the catastrophic breakage rate that had plagued earlier models. The crews who operated Panthers developed absolute confidence in their machine's capabilities. This confidence was built on repeated combat success across multiple theaters. On the Eastern Front, Panther battalions consistently achieved kill ratios of 5-to-1 or better against Soviet armor. Experienced crews learned to exploit the present tank's strengths, engaging from long range where the superior optics and gun performance gave overwhelming advantage, using hull-down positions to maximize the effectiveness of the frontal armor while minimizing exposure of the thinner side plates. The Panther's 7.5 cm KWK 42 gun was a masterpiece of German engineering. The long barrel, 70 calibers in length, giving a total barrel length of 5.25 meters, provided exceptional muzzle velocity. With standard Panzergranate 3940 armor-piercing capped ballistic capped ammunition, the gun achieved a muzzle velocity of 925 meters per second. This high velocity translated directly to armor penetration, with the ability to defeat 138 millimeters of armor sloped at 30 degrees at 1,000 meters. German optical equipment was superior to Soviet equivalents and comparable to American gear. The gunner's Turmzielfenrohr 9 monocular sight provided 2.5 times magnification with a clear field of view. Experienced gunners could identify and engage targets at distances where opposing tanks could barely see the Panther, let alone return effective fire. The commander's position included 6 periscopes providing all-around vision and a rotating cupola that allowed him to maintain situational awareness while directing the crew. The combination of protection, firepower, and adequate mobility created a tank that dominated most tactical situations it encountered. Soviet 3485s, introduced in 1944 with an upgraded 85mm gun, still struggled against the Panther's frontal armor at typical combat ranges. American M4 Shermans, the primary Allied medium tank in the West, were outmatched in direct engagement. The Sherman's 75mm M3 gun could penetrate approximately 91mm of armor at 500 meters, insufficient to reliably defeat the Panther's frontal aspect, even at close range. German tank crews knew these numbers. They had internalized the performance characteristics of their vehicle and their opponents' vehicles through intensive training and hard combat experience. A Panther crew engaging Shermans or 34s from favorable positions could expect to dominate the engagement, destroying enemy tanks, while remaining effectively immune to return fire, provided they maintained frontal aspect and used terrain intelligently. This confidence was not mere propaganda or national arrogance. It was based on measurable, repeatable combat results. Panther battalions in Normandy, despite being outnumbered and often operating with limited fuel and ammunition, inflicted severe losses on Allied armored formations. During the fighting around Villers-Bocage in June 1944, a single Panther company destroyed over 30 Allied tanks in a series of engagements spanning 3 days. At Aracourt, in September 1944, Panthers of 5th Panzer Army engaged elements of the U.S. 4th Armored Division, claiming over 40 American tanks destroyed for the loss of 14 Panthers. The crews who survived these engagements came away with unshakable faith in their vehicle. They had personally witnessed their gun defeating enemy armor at long range. They had felt the confidence that came from knowing that frontal hits from enemy weapons would likely bounce off or fail to penetrate. They had experienced the terror of being outnumbered 5-to-1 or 10-to-1 and surviving through superior equipment and training. Oberleutnant Klaus Becker had been one of those confident crews. His Panther had survived Kursk, survived the retreat through Ukraine, survived Normandy. He had personally destroyed 8 Soviet tanks and 11 American vehicles. He had been hit 7 times by enemy fire that failed to penetrate. The mathematics of armored warfare, as he understood them, favored his survival. The protection his tank provided was not theoretical, it was proven through repeated combat validation. Now, standing in that tent in Normandy, looking at a Panther that had been penetrated through its thickest frontal armor, Becker confronted a different mathematics. The American captain was not boasting or exaggerating. The evidence was physical, undeniable. Something had changed in the equation of armored combat, and the change was not in Germany's favor. The American captain led Becker to a makeshift testing ground where several captured German tanks sat alongside American vehicles. A team of ordnance specialists had been conducting systematic firing tests, documenting the performance of various American guns against German armor. The results were compiled in thick binders filled with ballistic data, penetration measurements, and photographic evidence. This was not propaganda. This was engineering analysis conducted with scientific rigor. "We need you to understand what you faced," the captain said, opening one of the binders. "Not because we want to demoralize you, but because your technical knowledge can help us understand why your tanks failed in ways your high command may not have anticipated." The binder contained firing test results from Aberdeen Proving Ground in Maryland, where American ordnance engineers had been testing captured Panthers since August 1944. A Panther Ausführung G, essentially identical to the model Becker had commanded, had been subjected to systematic firing trials using various American guns at measured ranges. The documentation was meticulous. Each shot was photographed, measured, analyzed. Penetration depth was recorded. Armor failure modes were categorized. Metallurgical samples were taken from areas surrounding penetrations. The 75mm gun from the M4 Sherman, firing standard M61 armor-piercing capped ammunition, had achieved penetration of the Panther's side armor at ranges up to 800 meters. Against the frontal glacis plate, the 75mm rounds had indeed failed to penetrate at normal combat ranges, confirming what Becker already knew. The Sherman's gun was inadequate for frontal engagement of the Panther. But then came the results from the 76mm Mohn gun, mounted in the later Sherman variants, like the M4A38. This longer, higher-velocity gun fired a heavier projectile at increased velocity. The test results showed frontal glacis penetration at ranges of 500 meters and below. The margin was thin, the penetration not guaranteed with every shot, but possible. More concerningly, the 76mm gun could reliably penetrate the Panther's turret front at ranges approaching 800 meters. Becker studied the photographs. The penetrations were clean, characteristic of projectiles with sufficient energy to defeat the armor completely rather than barely penetrating. The American engineers had achieved this performance through a combination of improved metallurgy in their projectiles and higher muzzle velocities from longer gun barrels. The Germans were not the only ones improving their weapons based on combat experience. Then the captain turned to the section documenting the 90mm M3 gun. The data was devastating. At 1,000 meters, the 90mm armor-piercing 33 round penetrated 170 millimeters of homogeneous rolled armor plate against face-hardened armor, which was harder on the surface but softer in the core. Penetration was actually greater in some cases because the projectile's hardened penetrator could break through the face hardening and then defeat the softer backing material. The Panther's frontal turret armor, 110 millimeters at its thickest, offered no meaningful protection. The upper glacis plate, 80 millimeters thick, but sloped at 55 degrees, for an effective thickness of approximately 140 millimeters, was within the penetration capability of the 90mm gun at combat ranges. Even the lower glacis plate, 60 millimeters thick, could be defeated at ranges exceeding 1,500 meters. The test photographs showed Panthers that had been engaged frontally by 91mm guns. The penetrations were catastrophic. Unlike the marginal penetrations sometimes achieved by 76mm guns, where a round might barely penetrate and cause limited internal damage, the 90mm rounds went through with tremendous residual energy. The projectiles didn't just penetrate the armor, they created massive spalling on the interior surface, sent fragments of the penetrator ricocheting through the crew compartment, and often continued through to exit the opposite side of the tank. One photograph showed a Panther that had been hit in the frontal turret face. The entry hole was nearly 4 inches in diameter. The interior of the turret was visible through the penetration. The American annotations noted that the round had struck at 820 meters range, penetrated completely, killed the gunner and loader instantly from spalling, and fragmentation, continued through the turret basket, and exited through the turret rear after striking the radio equipment. The commander had survived only because he had been standing in the cupola with his head outside the tank when the impact occurred. Becker had seen men die in tanks. He had pulled bodies from burning vehicles, but seeing the cold engineering analysis of exactly how the armor he had trusted could be defeated, seeing the mathematical certainty of penetration at ranges where he would have felt completely safe, fundamentally altered his understanding of the combat environment he had been operating in. The M26 Pershing heavy tank, the captain continued, mounts this 90mm gun in a fully traversable turret with gyrostabilization for the vertical axis. The tank weighs 46 tons, slightly heavier than your Panther. The frontal armor is 102mm on the upper glacis, sloped at 46 degrees. The turret front is 114mm. When our Pershings meet your Panthers, the engagement favors us significantly. Becker did the calculations in his head. His Panther's gun, the 75mm KWK-42, could penetrate approximately 138mm of armor sloped at 30 degrees at 1,000 meters. The Pershing's frontal armor, when accounting for slope, presented an effective thickness of approximately 145mm. It was marginal. Frontal penetration would be possible but not guaranteed, highly dependent on range, impact angle, and ammunition type. Meanwhile, the Pershing's 90mm gun could penetrate his Panther's armor with near certainty at any range where accurate fire was possible. The tactical implications were clear. In a frontal engagement between a Pershing and a Panther at typical combat ranges of 500 to 1,000 meters, the American tank had overwhelming advantage. "How many of these tanks do you have?" Becker asked, though he suspected he would not like the answer. The captain smiled without humor. "The M26 is just entering production. We have approximately 20 in Europe as of this moment, deployed for field testing with armored units. But the M36 tank destroyer, which mounts the same 90mm gun on a lighter chassis, we have over 1,000 in production. They're being delivered to tank destroyer battalions throughout the European theatre at a rate of approximately 150 per month. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this." Becker absorbed this information in silence. 1,000 tank destroyers mounting guns that could destroy Panthers from the front at ranges where return fire was marginally effective at best. The Americans were not deploying these vehicles in small, specialized units. They were equipping entire battalions with them, creating a fleet of Panther killers that would fundamentally change the tactical balance on the battlefield. The captain was not finished. He pulled out another binder, this one containing production statistics. "You need to understand the scale of what you're facing. In 1944, through October, Germany produced 4,200 Panthers. This is the best medium tank in your arsenal, and you've built just over 4,000 in 10 months. In the same period, the United States produced 17,500 M4 Sherman medium tanks. The ratio was more than 4 to 1. Becker knew that Germany was outproduced by its enemies, but seeing the specific numbers made the disparity undeniable. Even if the Panther was superior to the Sherman in direct combat, which the testing data suggested was true when engaging the 75mm armed variants, the numerical advantage the Americans possessed was overwhelming. "But that's not the complete picture," the captain continued. "Your Panther uses a Maybach HL 230 engine producing 700 horsepower. That engine requires precision machining, specialized alloys, and skilled assembly. Each engine takes approximately 200 man-hours to produce. Our Ford GAA engine in the Sherman produces 450 horsepower from a simpler design using more common materials. Assembly time is 60 man-hours per engine. We can produce engines 3 times faster than you can, and we have more factory capacity dedicated to engine production." The metallurgical analysis was equally revealing. American ordnance engineers had cut samples from captured Panther armor and subjected them to detailed testing. The armor quality varied significantly, depending on when and where the tank had been manufactured. Panthers built in 1943 showed excellent armor quality, with proper face hardening and good backing material. The steel had the correct carbon content, proper heat treatment, and uniform structure. Panthers built in late 1944 showed declining quality. The face hardening was inconsistent. Some plates showed inadequate hardness on the surface, making them more vulnerable to penetration. Others showed excessive brittleness, causing the armor to crack rather than deform when struck by high-velocity projectiles. The backing material in some samples showed inclusions and impurities that weakened the overall structure. The American captain explained the findings with the clinical detachment of an engineer discussing structural failures. Your armor quality has declined because you're running short of the alloying elements needed for proper steel production. Molybdenum, nickel, manganese, these materials improve armor performance significantly. Your access to these materials has been restricted by our strategic bombing campaign and by the loss of territories where these resources were mined or processed. Becker knew this was true. He had heard discussions among technical officers about material shortages. Replacement parts for tanks were increasingly difficult to obtain. New tanks arriving from factories sometimes had visible defects that would have been unacceptable in earlier production. The entire German war economy was under strain, and that strain manifested in declining quality of the very equipment soldiers depended upon for survival. The American opened yet another binder, this one containing photographs of German tank factories. Becker recognized some of the images. These were aerial reconnaissance photographs taken by Allied aircraft flying over German industrial centers. The level of detail was remarkable. Individual buildings could be identified. Damage from previous bombing raids was visible. New construction and repair work showed clearly. We know where every Panther factory is located, the captain said. Mahn in Nuremberg, Daimler-Benz in Berlin, Maschinenfabrik Niedersachsen-Hannover, Henschel in Kassel. We've bombed all of them repeatedly. We've destroyed machine tools, killed skilled workers, disrupted supply chains for critical components. Your peak Panther production was 380 tanks in July 1944. By December, we estimate you'll be producing fewer than 200 per month, and the number will continue declining. The captain paused, letting the implications settle. Meanwhile, our Sherman production in December will exceed 2,000 tanks, and we're ramping up Pershing production now. That field testing has validated the design. By spring of 1945, we expect to be producing 300 Pershings per month alongside continued Sherman production. Becker felt something fundamental shifting in his understanding. He had known Germany was losing the war in an abstract sense. The strategic situation was clearly deteriorating. Territory was being lost. Casualties were mounting. But knowing something abstractly and opercosa, confronting the specific material evidence of it, were different experiences entirely. The Americans were not just outproducing Germany, they were outproducing Germany while simultaneously developing superior weapons and maintaining higher quality standards in their manufacturing. The final element of Becker's education came when the American captain took him to observe a live-fire demonstration. A captured Panther Ausführung G, still in running condition despite damage to the turret, had been positioned on a firing range at a distance of 800 meters. American tank destroyers mounting 90mm guns were positioned at the firing line. We're going to show you what your tank crews faced when they encountered our 90mm guns, the captain explained. The engagement will be conducted at typical combat range under conditions similar to what would be experienced in actual battle. We want you to observe the results. The first round fired was an M82 armor-piercing capped ballistic capped projectile, the standard anti-tank ammunition for the 90mm gun. The report from the gun was sharp and loud, distinctly different from the tame eeper sound of the Panther's own weapon. The round struck the Panther's frontal glacis plate slightly to the left of center. Even at 800 meters, even through binoculars, the result was visible. The projectile penetrated cleanly. A spray of fragments and spalling erupted from the opposite side. of the tank. The second round targeted the turret front. Again, clean penetration. The projectile entered through the mantlet, one of the thickest armored areas on the entire vehicle, and exited through the turret rear. If there had been a crew inside, they would have been killed instantly from the combination of penetration fragments, spalling, and the projectile itself passing through the crew compartment. Additional rounds were fired at different aspects of the tank. The side armor, 60 mm thick, was penetrated at ranges exceeding 1,200 meters. The turret side armor was defeated at even greater distances. Only when the tank was engaged from angles approaching 90 degrees from the frontal aspect, where the side armor was presented at extreme obliquity, did some rounds fail to penetrate fully, and even then, the damage was severe enough that the tank would have been disabled, and the crew likely wounded or killed by spalling. Becker watched the demonstration in silence. Each impact, each penetration, each catastrophic failure of armor that was supposed to provide protection, reinforced the same lesson. The Panther's protection, which had seemed so formidable against Soviet and early American guns, was inadequate against the weapons now entering service. The confidence he had built through 2 years of combat, the faith in his tank's ability to keep him alive, had been based on facing inferior weapons. When the Americans deployed superior guns in sufficient numbers, that confidence became a liability rather than an asset. The American captain seemed to understand what Becker was experiencing. "Your Panther is an excellent tank when compared to our Shermans armed with 75 mm guns. Your crews are well trained. Your tactics are sound. But wars are not won by tactical excellence alone. They are won by nations that can produce superior weapons in overwhelming quantities, while simultaneously maintaining the industrial capacity to continue improving those weapons based on combat feedback. We can do this. Germany cannot. That is why you are losing." The demonstration ended. Becker was escorted back to the tent, where he would be processed for transfer to a formal prisoner of war camp. The American captain shook his hand before he left, a gesture that surprised him. "You're a good engineer and a good soldier," the captain said in German. "None of this is your fault, but someone needs to understand what actually happened out there, why so many of your crews died in tanks they thought would protect them. Maybe someday you can tell that story." Becker spent the next 7 months in a POW camp in northern France, then in England. He was repatriated to Germany in May 1945, returning to a country that barely resembled the nation he had left to fight for. The cities were rubble, the industrial capacity that had produced Panthers and Tigers, and all the machinery of war was destroyed. Millions were dead. The Reich that was supposed to last 1,000 years had collapsed in 12. He never commanded a tank again. In the years after the war, he worked as a mechanical engineer in Stuttgart, helping rebuild Germany's civilian industrial capacity. He designed diesel, engines for trucks and tractors, applied his knowledge of metallurgy to civilian manufacturing, taught a generation of young engineers who had no memory of the war. But he never forgot the lessons learned in that tent in Normandy. He never forgot the mathematics of industrial warfare, the brutal calculus that determined which nations survived and which collapsed under the weight of their own strategic miscalculations. In interviews conducted decades later, when historians sought out veterans who could explain the technical aspects of armored warfare, Becker spoke carefully about his experiences. He praised the Panther as an engineering achievement, which it was. He acknowledged the skill and courage of the crews who fought in them, but he was unflinching in his analysis of why Germany lost the tank war despite producing what many considered superior designs. "We built a very good tank," he said in an interview recorded in 1973, his voice still carrying the precise diction of an engineer. The Panther could defeat almost any Allied tank in a direct engagement at typical combat ranges. But the Americans built a good enough tank, and they built it in numbers we could never match. Then they built a better tank, the Pershing, and they were prepared to build thousands of those as well. We were fighting an opponent that could absorb our advantages through sheer production capacity, then overcome those advantages by developing superior weapons while maintaining that production capacity. That is a war that cannot be won through tactical excellence or superior engineering alone. The interviewer asked him about the moment he understood Germany would lose. Becker paused for a long time before answering. When the American captain showed me the production numbers, when I understood that they were building 20,000 tanks while we were building 4,000, and their tanks were getting better while ours were getting worse because we were running out of materials. A Panther could destroy 5 Shermans, 10 Shermans. But there would always be an 11th and a 12th, and eventually a Sherman armed with a 76mm gun or a Pershing with a 90mm gun. Mathematics is unforgiving. We could not kill them faster than they could build replacements. The American 90mm gun that had so devastated the Panthers at Aracourt and elsewhere represented more than just superior ballistics. It represented a fundamental difference in how the American military-industrial complex approached the problem of armored warfare. German tanks were often over-engineered, incorporating complex systems that provided marginal performance improvements at the cost of manufacturing difficulty and maintenance challenges. The Panther's interleaved road wheel suspension provided excellent ride quality, but was notoriously difficult to maintain. Changing an inner road wheel required removing multiple outer wheels, a process that could take hours under field conditions. The Tiger's overlapping road wheels suffered the same problem, compounded by the tendency for mud and debris to freeze between the wheels in winter conditions, immobilizing the tank until crews could thaw and clear the tank mechanisms. These were engineering decisions that prioritized performance over maintainability, made by designers who assumed that superior quality would compensate for inferior quantity. American designers made different choices. The Sherman's suspension was simpler, easier to maintain, and could be serviced quickly by crews with basic tools. The vertical volute spring suspension system was not as sophisticated as the Panther's interleaved wheels, but it was robust and reliable. When components failed, they could be replaced in the field without specialized equipment. This philosophy extended throughout the entire vehicle. The Ford GAA engine could be removed and replaced as a complete unit in a matter of hours. Track blocks could be swapped out individually. The transmission, while not as elegant as German designs, was simple enough that field mechanics could repair it without sending the tank back to depot-level maintenance facilities. This maintainability translated directly to operational availability. A Sherman that broke down could be returned to service within hours or days. A Panther with similar mechanical problems might be out of action for weeks waiting for specialized parts or skilled technicians. In a war of attrition where the side that could keep more tanks operational would gain decisive advantage, the Americans' philosophy of good enough engineering combined with excellent maintainability proved superior to German pursuit of technical perfection at the cost of complexity. The 90mm gun itself was a product of this same philosophy. It was not the most advanced anti-tank gun design theoretically possible. It was a proven naval anti-aircraft gun that had been adapted for anti-tank use by developing appropriate ammunition. The development time was measured in months rather than years because engineers were working with an existing, proven design rather than creating something entirely new. When combat experience showed that a more powerful gun was needed to defeat heavy German armor, the Americans had a solution ready for rapid deployment. By contrast, German development of improved tank guns was hampered by resource constraints, competing priorities, and an industrial base that was increasingly disrupted by Allied bombing. The 88mm KABK 43 gun mounted on the Tiger II was a formidable weapon. But the Tiger II itself was produced in such small numbers, only 492 were built during the entire war, that its impact on the battlefield was negligible at the strategic level. Individual Tiger II tanks might dominate local engagements, but they could not influence the overall course of the war because there were simply too few of them. The mathematical reality of industrial warfare asserted itself with brutal efficiency. Germany's tank production peaked at approximately 630 tanks per month across all types in December 1944. American production in the same month exceeded 2,000 tanks. Soviet production exceeded 2,500 tanks. Germany was facing enemies who collectively were building more than 4,000 tanks monthly, while German production was constrained by material shortages, labor shortages, disrupted supply chains, and systematic destruction of manufacturing facilities by Allied bombing. Quality could not overcome that quantity. German tanks achieved impressive kill ratios throughout the war. Panthers regularly destroyed 5 or more Allied tanks for each Panther lost. Tigers achieved even higher ratios in some engagements. But those ratios were insufficient when the Allies could replace their losses within days, while German losses took weeks or months to replace, if they could be replaced at all. By early 1945, many German armoured units were operating at a fraction of their authorised strength. Fuel shortages meant that tanks which were mechanically functional could not be deployed to combat zones. Ammunition shortages limited the number of rounds each tank carried. Replacement crews were increasingly poorly trained as experienced tankers were killed, faster than new crews could be properly prepared. The qualitative advantage German armour had enjoyed in the early war years had been eroded by attrition, material shortages, and the deployment of Allied weapons systems specifically designed to counter German heavy armour. The legacy of the Panther tank is complex. In purely technical terms, it was one of the finest medium tanks produced during World War II. Its combination of protection, firepower, and mobility was exceptional for a vehicle in its weight class. Panthers commanded by experienced crews in favourable tactical situations were nearly unstoppable. Numerous accounts from Allied tankers describe the fear and frustration of engaging Panthers, watching rounds bounce off the sloped armour while German guns destroyed Allied tanks with single shots. But technical excellence did not translate to strategic success. The Panther program consumed resources that might have been used to produce larger numbers of simpler, more reliable tanks. The complexity of the design meant that production was slower and more difficult than it might have been with a less ambitious vehicle. The maintenance requirements strained German logistics and reduced operational availability. And ultimately, the weapons systems deployed to counter the Panther, the 76mm gun, the 17-pounder, and especially the 90mm gun, proved that armour protection could be overcome through improved ammunition and higher velocity guns. For Klaus Becker, the personal legacy was a hard-earned understanding of how wars are actually won. He had gone into combat believing that superior German engineering and the tactical excellence of German crews would be sufficient to achieve victory. He had commanded a machine that was, by many measures, the best medium tank in the world during the period he fought, and yet he had watched his country lose the war because industrial capacity and resource availability mattered more than tactical superiority. His testimony, preserved in archives and historical interviews, provided valuable insights for historians studying the armoured warfare of World War II. He could speak authoritatively about the Panther's capabilities and limitations because he had commanded them in combat across multiple fronts. He could explain the tactical doctrine that German crews employed because he had been trained in those methods and had used them successfully. And he could articulate why those advantages were ultimately insufficient because he had been forced to confront the evidence directly in that tent in Normandy, looking at Panthers that had been destroyed by weapons his training had told him were inadequate. The 90mm gun that destroyed his confidence in German armour superiority went on to a long service life. The M36 tank destroyer, equipped with the 90mm gun, served through the end of World War II and into the Korean War. The gun, itself, mounted on various platforms, remained in American service well into the 1950s. It proved effective against North Korean 3485s during the Korean conflict, demonstrating that a weapon system designed to defeat German heavy armour in 1944 remained relevant against Soviet-designed tanks in 1950. The Pershing tank, which mounted the same 90mm gun in a turreted configuration, arrived too late to significantly impact World War II in Europe. Only 20 Pershings saw combat before Germany surrendered in May 1945. But the design formed the basis for American tank development in the post-war period. The M46 Patton, developed directly from the Pershing, served as the main American medium tank in the late 1940s and early 1950s. The lineage continued through the M47 and M48 Patton tanks, which incorporated the lessons learned from Pershing combat testing and featured continued refinements of the same basic design philosophy that had made the Sherman successful: good enough performance, excellent reliability, and designs optimized for mass production and field maintenance. For the tank crews on both sides who fought in the final year of the war, the deployment of the 90mm gun represented a shift in the tactical calculus of armored combat. German crews, who had grown accustomed to frontal immunity when engaging, Shermans, armed with 75mm guns, found that immunity stripped away when facing 90mm guns. The psychological impact was significant. Crews who had felt relatively safe in hull-down positions were forced to recognize that no position offered guaranteed protection. The Americans had developed a weapon that could defeat German heavy armor at ranges where accurate fire was possible, and they were deploying that weapon in numbers sufficient to fundamentally alter the battlefield dynamics. Allied tank crews experienced their own shift in perspective. Crews who had felt outmatched by Panthers and Tigers, who had relied on numerical superiority and tactical flanking maneuvers to overcome German armor advantages, suddenly had access to a weapon system that could engage German tanks frontally with confidence of penetration. The reports from crews operating M-36 tank destroyers in late 1944 consistently noted the effectiveness of the 90mm gun against all German armor. Panthers were no longer invulnerable threats requiring elaborate tactical solutions. They were simply targets that could be engaged and destroyed, using standard gunnery procedures. This democratization of anti-tank capability had strategic implications beyond the immediate tactical advantages. When only specialized units with limited production weapons could reliably defeat German heavy armor, German tanks could achieve local tactical successes by focusing on sectors where those specialized units were not present. Once 90mm guns became widely available across multiple battalions and divisions, German armor lost the ability to exploit gaps in Allied anti-tank capabilities. Everywhere Allied forces operated, they had weapons that could defeat the best tanks Germany could field. The war in Europe ended less than 8 months after Klaus Becker sat in that tent examining the destroyed Panthers. The final German offensives in the West, including the Ardennes offensive in December 1944, demonstrated that German armor could still achieve tactical successes under favorable conditions. Panthers and Tigers destroyed hundreds of American tanks during the Battle of the Bulge, but the offensive ultimately failed because German forces could not sustain their advance in the face of Allied numerical superiority and air power. The tanks that had seemed so formidable in individual engagements could not overcome the strategic reality of a collapsing front and an enemy that could replace losses faster than Germany could inflict them. Becker lived until 1991, long enough to see Germany rebuilt, to witness the Cold War, and to see the fall of the Berlin Wall. He outlived the political system he had fought for by more than 4 decades. In his final years, he occasionally spoke to students and historians about his experiences, always emphasizing the same themes. Superior. Technology alone does not win wars. Industrial capacity and resource availability determine which nations can sustain prolonged conflicts. The courage and skill of individual soldiers matters, but it cannot overcome fundamental material disadvantages. These were lessons he had learned through personal experience, through the deaths of crews he had commanded, through the moment he stood before a destroyed Panther and understood that everything he had believed about his tank's invulnerability was based on facing inferior weapons. The story of the Panther tank and the 90mm gun that defeated it is ultimately a story about the nature of modern industrial warfare. It is a story about how confidence built on past success can become a fatal liability when the enemy develops superior capabilities. It is a story about the difference between tactical excellence and strategic viability. And it is a story about the brutal mathematics of attrition warfare, where production capacity and resource availability matter more than individual weapon performance. For Klaus Becker, the lesson came in a tent in Normandy, looking at evidence he could not deny. For thousands of other German tank crews, the lesson came in the final seconds of their lives, when rounds they thought their armor would stop came through and killed them. And for the nations fighting World War II, the lesson was written in production statistics and casualty figures that showed clearly which side could sustain the losses, and which side would eventually collapse under the weight of material inferiority. The Panther was an excellent tank destroyed by mathematics it could not overcome. The 90mm gun was a good enough weapon produced in quantities sufficient to guarantee success. That difference, repeated across every domain of the war, determined the outcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.